We have a rather straightforward proof today, but it's going to help illustrate two things. First of all, the reason it's straightforward is because it's a simple application of the definition of convexity and the definition of intersection. So remember, we don't just get the axioms in undefined terms. When we're dealing with Euclidean geometry, we get the basics of set theory and also the properties of real numbers. So the logic of proofs kind of comes along because of set theory. And so the idea of intersection actually has meaning in this context, even though we haven't defined it in our geometry terms. Also, the cool thing I'm going to show you is sort of a feature. Watch these orange and blue polygons as I click through. Watch them disappear and then reappear. So I'm going to show you how to create that effect after I do the proof. So the proof begins with two arbitrary polygons, polygon 1 and polygon 2. And of course, we're creating the intersection, which we'll call polygon 3, the green polygon there. And we're going to let 2 points, x and y, be arbitrary, but they have to be in the intersection. They have to be in the intersection or the proof doesn't work. So, if polygon 1 and polygon 2 don't overlap at all, well, we're done. So we have to have overlapping polygons here for the proof to even work. So we're going to we're going to notice that that x and y, they have to both be in polygon 1 and they both have to be in polygon 2 by definition of the intersection. So next step, because polygon 1 is convex, right? We know that the entirety of the line segment xy has to be inside polygon 1. Every point on this line has to be inside polygon 1. And that's just the definition of polygon 1 being convex. And then that's also true for polygon 2, that the entirety of the line segment is also inside polygon 2. So that means that the entirety of the polygon of the line segment is inside polygon 3. Because by definition of the intersection, right, if the entirety of the line segment is in polygon 1 and the entirety of this line segment is in polygon 2, then the entirety of the polygon must be in that intersection. And therefore we have the result that polygon 3 is convex because every point of xy was in polygon 3. And I haven't done the part about finishing this off with, hey, because x and y were chosen arbitrarily, this is true for all possible x and y. But again, that's part of the logic of the proof, and we generally leave that off, although it's good sometimes not to do every step. But that's the logic, because we're choosing things arbitrarily, right? We chose arbitrary polygon 1 and 2, and polygon 3 is arbitrary because it's the intersection of two arbitrary things. You don't really have a way to change polygon 3. And then x and y are arbitrarily chosen inside polygon 3. So since everything is arbitrary, this is going to hold for any possible convex polygons you can draw that have an intersection and any possible points x and y that you can place inside that intersection. So let's take a look at how the GeoGebra pieces work in this drawing. So the feature is that we can have the orange and blue polygons. They appear up here. So let's show you. So in step 1 they appear, right? And then in step 5 the blue one disappears because we're focusing on the orange one. Then for step 6, that does two things. The blue one reappears and the orange one disappears, and then the orange one reappears here. So let's just take a look at what's going on. So I did the blue polygon first, and we'll just go into its settings, go to advanced, and look at this. So this is kind of great for a theorem proving class because we have all the notation. GeoGebra actually reverts to the notation for logical symbols. So this reads, conditions show object, show it when M is true and R is not true. So this is M and not R, or S. Okay, so let's get this figured out, right? So I'll just show you um, that. Okay, we can come in here, right? So this is M. M is true. And then this one is R, so MNO, then P was used for something else, and then RST. Okay, so you can see that it is M and not R, right? So when R is true, the blue one goes away, and then or, I may have that wrong, S and T. So let's look, polygon 2 again, right? So M and not R, and then or S, okay? So you can see the R and the S doing it. So these two, right? This is R turning it off. That's the not R, and this is the or S turning it back on. So tons of fun there. And then the problem was, though, I had to do every single one of these pieces to get them to turn off too. But what I did was I got it right for the polygon itself, and then I just copy pasted that, and so that will actually show up. Now, a couple of things to let you know. You don't type it in like this. I typed in and M and not R, and not R is actually exclamation R. And the or, the way you get an or in there is you do two of the vertical bars. They're above the backslash key, above your enter key on your keyboard. And so those are what you do, and then when you to type them in, and then when you come back in, you'll see that they'll convert it to those symbols. And there is a you can just do GeoGebra logical operators. Google that to find a page, and I'll also try to link that for you, and be able to show that. Also, I want to show another little trick because you can see I accidentally moved this. So one good way to line all these things up is to show the grid. And sorry, I want to do major and minor grid lines. And so what's nice about dragging these around is they sort of snap into the grid. And when you get to, more larger text boxes, so I can I can let it snap to grid, and then I can use the up and down arrows to move it. And the up arrows move it pretty nicely, half a grid mark there. So that allows me to place these carefully. Now, the text boxes, and I'm a little baffled because I actually did this, and when I did this, these were snapping to the corners of a grid. So the grid has changed slightly since I saved this, and I don't know why. But these will snap to the corners. What they won't do is you can't use the up and down arrows or the left and right arrows to move them. Oh, and then when the up and down, left and right arrows move a fairly large amount, but you can do shift arrow and get a very minor amount. So let me see if I can show that. So this bottom one, here's the up and down arrow, just pressing it repeatedly. Here's shift up. And you see how long it takes to move. I'm hitting about every half second, I'm hitting the up, shift up, shift up, shift up, and it moves in such a tiny way, right? But I can get it to move a lot with just the up arrow. So those are some tips and tricks about using GeoGebra in this type of proof. I don't ask for them very often, but you are welcome to give me some likes and some comments. Again, there's a lot of pro tips in this video. So if they helped you out, then put a like down there or maybe a comment. And I'll be back with more proofs soon.